Hello, I'm Claire Penrose and I'm the General Manager of Asia Pacific at the Global CCS Institute. I'm part of the Institute's team working with governments, industry and a range of other stakeholders around the world to help successful demonstration of CCS technologies. I'd like to welcome our international audience as we have attendees from around the globe. Today's webinar will present findings from the ROAD project on CCS CO2 chain operations, as well as some recommendations for future CCS project operations. A few housekeeping matters before we start. This webinar will be recorded and it will be placed on the Institute's website along with the slides in the next few days. We'll also have an opportunity at the end of the presentation for questions from attendants. I'll now kick off by introducing to you our presenter and panellist. Our presenter today is Jan Uilenreef. He's the project manager with E.ON GDF Suez joint venture in the ROAD project. He is responsible for the design and engineering of the 16-inch CO2 pipeline connecting the capture plant and the injection platform. Jan has over 40 years of experience in the industry, including design and project development, project management of a variety of natural gas and CO2 pipeline and CO2 installations. Jan was previously responsible for several new build projects such as the OCAP CO2 pipeline. Our second panellist today is Dr. Andy Reid. Andy Reid is the Capture Director of the ROAD project. He is responsible for the engineering, design and construction of the capture plant, including the interfaces with the power station. Andy has an excellent understanding of power plant technology and the electricity markets associated with commercial constraints. Andy has 20 years of experience in the power industry, including design and operation of supercritical coal power plants, combustion technology and a stint on an operating coal-fired power station. All attendees are welcome to submit questions throughout the presentation through the Questions tab on the GoToWebinar control panel on your screen. The questions will be moderated and I'll pose the questions to Jan and Andy at the end of the presentation. Please be aware that we may not be able to answer all of your questions today. However, we will endeavour to get through as many questions as possible. As I mentioned, the webinar will be recorded and available on our website along with copies of the slides and the presentations in the next few days. And now, without further ado, let me hand over to Jan.
Good day, ladies and gentlemen. I'm honored to present to you an overview of the flow assurance work we have done for the ROAD project. I'm sitting together with Mark Kombering, our communication manager, who's helped me with the slides. My intention is to tell you first a little bit and give you a little project overview, then the description of the pipeline route, the onshore and offshore part, then to explain the process chain from stack to well, and then to explain the control philosophy and the flow assurance study we did. And I will finish with a few research recommendations for the future. First, the project overview. In this slide, you see the total chain of plants that will be built for the ROAD at the Maasvlakte MPP3 power plant of E.ON. On the left of the slide you see the Maasvlakte power plant, which produces 809 tons per hour CO2, which is directed to the stack. From the stack, the capture plant that will be built by ROAD takes 198 tons per hour CO2, of which 170 tons is fed to the compressor, and before it's fed into the pipeline and transported to the P18A TACA platform in the North Sea. The CO2 is cleaned in absorbers, and at the end a mixture will come out with the composition as is seen in the bottom, and it is so you can see it's mainly CO2. By the way, ROAD is a 50-50 joint venture of E.ON and Gaz de France, and they are planning to build the capture plant and the compression and transport system in the near future. Here you see the area where we are talking about. In the middle you see the Aeon plant of the Maasvlakte, on the old Maasvlakte. On the left there is the new Maasvlakte that is at the moment being built and is almost ready to accept the ships. From the Aeon plant we have a route onshore over the Maasvlakte, and then we pass the shipping lane of where all the ships into Rotterdam go, and then we have a 20 kilometers pipeline to the Taker gas field in North Sea. As you can see, it's even closer to The Hague than to Rotterdam, because Rotterdam is somewhere here and The Hague is here. This is the beginning of the pipeline. It is the Aeon power plant under construction, and the red area is the area where the capture plant will be built, and which is indicated on the right. The green is the capture plant, and the purple is the compressor house. Then we go to the pipeline routing. Before we look at the route, I will tell you some data about the pipeline. It's basically a 16-inch pipeline, which is 400 millimeters in metric. It has a mechanical design pressure of 140 bar, which is rather high for pipelines. Normally, it's in Holland at least around 80-90 bar. The mechanical design temperature is from -10 and to +80, so the pipeline can be hot, and I will explain later why that will be. The wall thickness is calculated at about 20 millimeters. Some parts are a little thicker, but on average is around 20 millimeters. As the municipality of Rotterdam requires, the soil cover should be minimum 1 meters, so it's buried in the pipeline corridor of Rotterdam. The onshore part is insulated with polyethylene of 50 millimeters, and the offshore pipeline is insulated with 30 millimeters of the same material. Why there's a difference, I will explain to you later. The route has two horizontal directional drillings, very long ones, about 1500 meters long, and they're made of a pipe-in-pipe system with a vacuum in between the two pipes, because drilling with an insulation does not guarantee a good insulation, so the vacuum that is in between the pipes gives a better insulation. And the depth of both the Yangtze Harbor and the Maasvlakte is about 38 meters below sea level, below the Dutch reference sea level. Here is a little movie that Mark made about how the pipeline route is shaped, and I will start it and you can see how it's going. We started the road plant, and then the pipeline is running over the road side till it reaches here at the cursor. It reaches the pipeline corridor of Rotterdam, and it follows the pipeline corridor till it reaches the Yangtze Harbor. This is the Yangtze Harbor. Under the Yangtze Harbor there's a directional drilling, and the directional drilling is coming above ground past the Euromax area, where this is a container harbor where a lot of containers are stored. So we pass under the Euromax area. From there on we go into the leading corridor again, follow the route and to the border of the Maasmond, where we have another directional drilling. This is the directional drilling under the Maasmond. It's also 40 meters deep, so to make sure that all the ships that reach Rotterdam do not have any problem with the pipeline. And from there on the pipeline continues in the seabed with a coverage from 1 meter to the Taker platform, which is located here. You will see it in a minute. It gives you a nice idea how the pipeline runs. The offshore part is about 20 kilometers. There's the Taker platform. Now you can imagine how it looks. Huh? I don't know where it stops, sorry. To take a closer look at the onshore part, you see here the Youngster Harbor, which was not yet finished when we made this picture, but now this has been taken away, so it's now a real harbor. And this is the Maasvlakte. This is the entrance to the Rotterdam harbor, where the big ships can enter and go into the new Maasvlakte to deliver their cargo. The Aeon plant is here. As I have told, the pipeline can be operated on high temperature, and that is mainly in the beginning of the storage period. It means that the pipeline will be hot, about 80 degrees, and since it is constructed at the temperature of 10 degrees, it means that there will be a tremendous expansion of the pipeline in operation. And to cope with that expansion, the pipeline is equipped with expansion loops, and because of the stiffness of the pipe, these expansion loops have to have a big size, as you can see here. This leg is 6 meters, this leg is 8 meters, then again 6 meters back. And because the pipeline corridor is used very effectively with a small distance between the pipes, 400 millimeters, the expansion loop has to go under the future pipelines to make sure that there's an efficient use of the pipeline corridor. And you can also imagine that when the pipeline is hot, these pipelines are in the warm zone, and that's why the insulation of the onshore pipeline is thicker than the offshore pipeline to protect the other pipes that will be constructed above our pipeline. This is a picture of the Maasvlakte crossing. It is a very interesting crossing. It's a very long, deep crossing. First, a small hole will be drilled under the Maasvlakte. When you reach the other side, there is also an additional drilling made for the mud return line. So when the small hole is ready, the hole is reamed and is supported with mud so that it doesn't collapse, and the mud is returned through the mud return line to the shore. The sand is taken away and the mud is reused till the hole has the size that's required to pull the line. In the meantime, the line is constructed here on the onshore, and it's pulled through the hole with the ship from offshore. This is the ship is the pulling mechanism to pull the line. At the end of the pipeline, there is the Taga platform that is shown here, and you can see at the horizon there's the Maasvlakte, so it's a rather small distance. It's about 20 kilometers, and the platform is located on the gas field on this location, and the well we are using is the P18 here, which has a volume of about 7 to 8 million tons, which we use first to store the first batches of CO2. The well itself is indicated here. It is a 5.5 inch well pipe. There's an internal pipe with a restriction in the bottom, and you should keep in mind that there is a restriction because this causes pressure drop and velocity increase, which is important for the design of the flows through the well. Interesting is also that here you see a subsurface safety valve that can shut off the well in case something happens. Okay. Then we go to the control velocity itself and the flow assurance. First, some facts and figures. The Aeon Maasvlakte power plant has an output of 1,700 megawatt, and this is firing coal, and green, we call it firing coal, with an efficiency of 46%. It's operational, it's presently in startup phase, and expected operational will be this year or the next year. And there are already equipment is installed to make sure that the capture plant can smoothly be connected to the Maasvlakte power plant. The capture plant is a post-combustion capture plant. That means that the CO2 is removed after the combustion of the fuels. It has a capacity of 250 megawatt equivalent, so it's about a quarter of the output of the Maasvlakte plant. The capture volume is 1.1 metric tons per year, and it means a maximum design flow of 47 kilograms per second. And when we use this flow, you can see that the reservoir is in about 6.5 years. The reservoir that is available to us, the P18A, is filled in about 6 to 7 years. The transport capacity is in the 16-inch pipeline is 1.5 million tons of gas per year. While in the dense phase, 5 million tons per year can pass through the pipeline. The storage area is a depleted gas reservoir of Taka. It has a capacity of around 8 million tons, which is sufficient to have this storage time. And we will start filling the reservoir when the pressure has dropped to 10 to 20 bars. It's also depending on what moment we are ready to build the plant. I have repeated the CO2 composition here. You can see it's almost pure CO2 in the CO2, and it means that the thermodynamical properties of pure CO2 can be used to describe the flow and the thermodynamic properties. The transport and storage system is schematically indicated here. The CO2 is coming from the capture plant, from the CO2 stripper. So the liquid that is saturated in CO2 is heated, and CO2 comes out and is collected in this accumulator where the water falls out, and the CO2 gas leaves over the top into the suction of the compressor. From there on, the compressor compresses it to, let's say, about 100 bar and feeds it into the pipeline into the reservoir. The compressor is an integrally geared compressor with 7 or 8 stages, and it has, after 4 stages, a drying unit will be installed to dry the CO2 to the specification 50 ppm or less. The compressor is not controlling the flow of CO2. The flow of CO2 is controlled by the amount of CO2 that's taken out of the stack. The compressor makes sure that all the CO2 that is given to him will be compressed at the required pressure by the process, and the temperature is controlled by the cooling of the compressor discharge with this cooler. There are some controls around the compressor to make sure that he is able to have a steady operation with fluctuations in the feed and discharge. This is a medium flow bypass control to make sure that there's always enough and always sufficient CO2 going through the compressor, and in case there's not enough CO2 can pass, it can be returned to the CO2 absorber, so to give a smooth operation. After the compressor discharge, it's fed into the pipeline over about 25 kilometers, and then it reaches the platform, which is this situation, and it flows into the reservoir. This is a curve of an estimated curve of the compressor, and it shows how the control of the inlet guide vanes work. When a certain flow is required, you can vary the discharge pressure of the compressor by going into another angle of guide vanes, while the compressor can be turned down also by to go to a lower flow, also by going to another guide vane position. This is a combined curve of all the 7 or 8 stages. As we have no intermediate storage, the capture plant has closely to follow the operation of the power plant. And it means that the transport of storage equipment should also be designed such that the whole system can follow all the starts and stops and shutdowns and normal operation of the power plant. So we gave sufficient emphasis on normal operation, startup and shutdowns to make sure that the whole system has a sound and safe operation without any problems. As you might know, CO2 is a very sympathetic material. It has a very low critical pressure. That means under conditions that are reachable by us, you can go from vapor to liquid and to the dense phase. Dense phase is a thermodynamical status that represents a phase that is no liquid and no gas. It has the properties of both, and it is, you could say, it's a gas with a very high density or a liquid with a lower density, but it behaves like liquid. And when you let the gas CO2 flow through a pipe from the wellhead into the bottom, you have to apply high pressure at the wellhead to be able to store it at 20 around 20 bar in the wellhead. When you later on, when the pressure of the well increases, you transport in dense phase, and it means that then the pressure of the wellhead is lower than in the reservoir. It looks like the CO2 is falling into the reservoir, so the pressure here will be around 85, 90 bar, and you can even reach close to 300 bar down in the reservoir because of the gravity, the gravity that pulls the CO2 into the well. And here you can see in the gas phase you have a low static pressure drop and a high velocity, and that causes a high friction pressure drop. In the dense phase you have a high static pressure drop, it's a heavy liquid, you have low velocity and a low friction pressure drop. And that is the mechanism that makes sure that we can, with a low pressure, can fill a high pressure reservoir. In this graph, it's assumed that there is only gas or only dense phase, but in practical there will be sometimes slugs. There's a mixture of gas and liquid will be formed in the pipeline, and when the slug, when the slug is reaching the wellhead, it falls down the well piping, and it will, because of the pressure is changing over the length of the pipe, it will partly vaporize or condense, and it could cause vibrations in the well piping. So in our design we made sure that the vibrations in the well piping will be minimized. In simulations made with the Olga program have indicated that the temperature of the well piping can be very low, and since we have a design temperature of -10, we must make sure that we never come below -10, and that can be done by diminishing the quantity of CO2 that is flow into the reservoir, and especially in the low reservoir pressures, which is the blue color. It means that you have to feed with a lower flow to make sure that you don't reach temperatures below -10. Another limitation that is opposed to the well is the temperature of the downhole, because at plus 15 degrees CO2 tends to form hydrates 15 degrees and below. So we want to make sure that we always stay at the bottom of the well above 15 degrees. And another limitation that is opposed to us is the restriction in the hole. As you remember from the slide before, when you see the well piping, there's a restriction at the bottom, and this restriction gives a pressure drop and may cause vibration. So we must make sure that we have to stay within the temperature limitation and the vibration limits. The study has showed that that when we operate according to these lines, we will stay out of the region of the minimum downhole temperature and the mixed flow that could occur. When we have no platform control valve, that means when the pipe is open on the platform, then the chance of mixed flow are higher, and we have to stay at a high temperature to avoid mixed flow into the well piping, while using a platform valve, increasing the pressure of the pipeline a little bit, it will the limitation of only the downhole temperature will be valid. Adding a control valve at the wellhead, of course, will cost energy, but it will only cost energy in the beginning. But at the end of the operation, when the reservoir pressure is higher, you will gain it back, because instead of this pressure, you can operate at a long time at 85 bar, which gives a reduction of energy cost. When you combine the two graphs before, this is the operating envelope what we should use to make sure that we don't, in normal operation, don't get any problems with slugs, temperatures, and so on. So this is basically how the pipeline should be operated. Initially, the pipeline has to be hot, and then after maybe half a year, we can go to 40 degrees and stay on 40 degrees. The pressure is also high at the beginning because of the gas that has a higher friction loss in the pipeline and the well piping, and when the pressure is higher, we can stay at a lower pressure, 85, and at the end, when the pressure in the well is very high, then you have to increase the pressure to make sure you get everything in. This is a representation of how the operating lines function in the Mollier diagram. The Mollier diagram is a thermodynamical diagram which gives all the properties of CO2 projected in one plane. This is the area where vapor and liquid can exist together. This is the vapor area here, and above the critical point of 77 bar and 38 degrees, the CO2 is supercritical, and we call it has a dense phase. You see that the compressor starts with a very low pressure of the CO2 leaving the capture plant, and in 7 or 8 stages it is compressed to the required 85 to 90 bar at the discharge of the compressor. From there on, it's cooled to 80 or 40, depending on what operating phase you want to be in. And so this is the operating envelope where we normally would be. When you look at the continuation of the flow, you see here the point where the compressor has ended, and from here on, in the 20 bar case, this is the operating line to reach the 20 bar with avoiding this area of slugs, of vapor and liquid, which causes slugs, and with a higher head reservoir pressure, this is the operating line. This is the wellhead pressure and temperature, and this is the downhole temperature and pressure. And for 300 bar, this is the wellhead temperature and pressure, and this is the downhole temperature and pressure. In the operation, startup and shutdown, we always try to avoid this area of vapor and liquid, because that causes slugs and could cause low temperatures vibrations. This is another representation of the how the system works. It's worth to mention the temperature profile in the early stages of the operation. When the reservoir pressure is low, you have to start with a high temperature and to reach a downhole temperature of above plus 15 degrees to avoid hydrate formation. And you see that there is a large pressure drop in the bottom part of the well piping because of the restriction that you saw on the earlier slides. And here you can also see that from a low pressure, the heavy CO2 dense phase causes the high pressure at the downhole. This is the pressure profile, and it has the same shape, but the pressure drop is less than the tremendous temperature increase in the last sheet. When you when you have to shut down the plant, the pipeline is filled with one phase, and when you shut down the pipeline at the high pressure, it will cool down to the seabed temperature, which is around 4 degrees, and you might get a considerable amount of liquid. That is represented here. When you are here, you shut the pipeline will cool down according to this line. You will end up with a vapor weight fraction of 0.22. That means 78% of liquid. While when you heat up the pipeline before you shut it down, before you close it in, you go to here to, let's say, 80 degrees. Then when it cools down from 80 degrees, then you have only 42% liquid and 58% weight. So that means that when you operate it at higher pressure, so it's even better. And when you are when you have the possibility to close the valve at the compressor side and open and let the valve at the wellhead open, you can first heat the pipeline and then let the pipeline flow into the well and diminish the pressure. So it means that the pressure, you see that you cool down, you miss this vapor liquid and you end up probably here or there, but you don't come into the liquid. That means that when your pipeline is waiting on the seabed for the next start up, it will be only filled with vapor, and you can smoothly start up by pressurizing the pipeline in the vapor phase, going up, and then start the normal operating procedure. We have investigated all types of startups and shutdowns, and here is a representation of the plant shut off after a plant shutdown. It means that you have to shut off the pipeline, and we're able to fill it only with liquid, and then you have to pressurize the pipeline again, compress it with hot pipeline in contents with hot gas. You open the control valve slightly and let when you open the control valve at the pressure slightly above the wellhead, and you keep good track of the temperatures on top and below in the well piping to make sure that you stay within the limits that are given, and when all possible slugs are gone, you can increase the flow to the normal operating flow. Now this is the plant shutdown which I talked already. You heat the pipeline content to 80 degrees, and you empty the pipeline with a closed compressor valve into the well, and you close the well with the pressure control valve on the platform just before backflow from the well will occur. But this is not only planned startup and shutdown will happen. Sometimes there might be a non-planned shutdown because there is something wrong on the platform valve is closed. In that case, you're not able to empty the pipeline into the well, and then you have to decide what to do. Do I expect a long repair time? Then it's better to shut down the capture plant, and then the pipeline will be filled with liquid because it's cooling under pressure. When the pipeline is when the failure is repaired, you can start the pipeline on the slow speed to make sure that only small slugs are passed over the control valve, and when they're all gone you can speed up to normal operation. And when you expect a short repair time, just continue to fill the pipeline with hot CO2, and it might cool a little bit, but you can start up without any problems. When there's a problem at the capture plant, the compressor discharge valve will close. In that case, the pipeline is cooling down, and there might be a lot of liquid in the pipeline, and you should start with monitoring flow and temperature to make sure that there are no vibrations or temperature problems will occur. Finally, we have some few recommendations. It is recommended that to investigate the possibility that the CO2 can be injected without any heating, and to make sure that you can handle the slugs in the well piping. That is an advantage because then you will be able to transport CO2 to low pressure fields at a larger distance, because you can and at a reasonable cost, because you can transport all the time in the dense phase, and you can use a cold CO2 transport without insulation, which is a cheaper solution. This was my presentation. Thank you.
Thanks very much, Jan, for that excellent presentation. I'd just like to encourage everyone to submit your questions in English directly into the control panel, which should be on your screen now. We had one question early on in the presentation, Jan, which I think you sort of addressed later on, but I'll still pose it to you, which is, just explain the rationale for transporting the CO2 at up to 80 degrees Celsius.
Stay with the downhole temperature below +15 to avoid hydrate formation. You can work out that you have to start at a high temperature to make sure that due to the temperature losses, you never reach this low temperature.
Yeah.
Okay.
And maybe you can.
If I can. Yeah, I can add something. I mean, one of the issues is that we have, to begin with, we have a very low reservoir pressure, and we have this narrow tailpipe at the bottom of the well, so we get a big pressure drop and a big Joule-Thomson cooling at the bottom of the well. And we want to keep the well warm enough that we won't get hydrates, and we certainly don't want ice. So, so we have to work backwards, basically, from the downhole temperature, and we have to operate the pipeline to begin with very warm. Okay, great. Thanks very much for that. Right, the second question I've got here is that CO2 with water is very corrosive. What are the materials that you're using for the pipeline and the well, and do you take into account the corrosion rate and life duration?
Now the CO2 is indeed, CO2 and water are indeed very corrosive, but it's only when the CO2 is present as pure water, and not as long as the CO2 is dissolved in the CO2, the water is dissolved in the CO2. and the quantity of water we allow in the CO2 is such that it will always be dissolved in the CO2, so no corrosion will take place. That's why we're using plain carbon steel for the construction material.
Okay.
We do have stainless steel in the well, because when the well's shut in, you will get reflux. So the well is designed to withstand CO2 and water corrosion.
That's it, yeah.
Yeah. Even then, we don't really expect it to happen, because once the well has been running for a while, we expect all the water to be pushed away from the well.
Okay, great. Thanks very much. All right. Our next question here is, why did Road decide a pipeline diameter of 16 inches? And was this size designed for a $1 million tonne per year operation?
Can I give the history of that? Yeah.
Sure. Go for it, Andy.
When we originally sized the pipeline, we hadn't done the detailed work on the reservoir and selected the individual reservoir P18-4 to start with, but we also need to cover we also need to be able to operate with P18-2, which has multiple wells. So in the design case for the pipeline, we don't have the high pressure drop across the well. And we have, and P18-2 is like P18-4, it starts at a very low pressure. So to begin with, we have to operate in the gas phase, and so the pipeline is sized to take 1.5 million tonnes per year in the gas phase. 1.5 million tonnes is the flow rate you get from the road plant if you operate 24 hours a day, 365 days a year. We know the power station shuts down, and sometimes commercially and sometimes for maintenance. We know that the capture plants won't be 100% reliable from day one, so we have chosen a 1.1 million tonnes a year as the average figure we think is achievable for the demonstration plant, and that's what's our sort of headline design case. But if we ran continuously, it would be 1.5, and so that's what the pipeline is designed for. So it's 1.5 million tonnes in the gas phase.
Okay, great. Thanks very much. The next question I've got here is, can you please clarify what the slugs are? I think you mentioned them a few times in the presentation.
It's CO2 on the phase line, so it's liquid and gaseous CO2.
Right.
Coexisting.
Okay,
like you have steam and water in a kettle that's boiling. You'll have vapor and liquid CO2.
Great. The next question is, how do you avoid two-phase CO2 flow in the pipeline?
By choosing the operating conditions above the critical point.
Mm-hmm.
So then you have only a single phase, and we do everything to avoid to come into the vapor liquid area. You can't always avoid it, but then we increase the pressure of the pipeline to make sure we stay away from the vapor liquid area. And when there are a small amount of slugs, we monitor the well very closely to make sure that they don't do any harm.
We generally operate either above the critical pressure or the critical temperature.
Yeah.
And the only time we do get slugs is on shutdown and startup, and that's because we lose control of the temperature, because the pipeline then cools.
Okay then. Now our next question, I think you touched on a little bit, it's just asking for another explanation, is what is the temperature pressure change from post-combustion capture to compressor to transport in a pipeline to the well storage?
The stripper operates at something like 1.5 to 2 bar. So the inlet to the first stage of compressor is 1.5 to 2 bar.
Yeah.
The pipeline is normally around 85 bar, although it does depend a little bit on the conditions. The reservoir will start at below 20 bar and will finish at 300 bar.
Okay, thanks for that, Andy. The next question is, when the reservoir pressure is very low, would it be possible that conditions in the well become such that it reaches the two-phase envelope?
Andy, maybe you could.
It will happen. Well, does it happen?
Difficult question. Huh?
Yeah, it shouldn't happen. It shouldn't happen during normal steady flow because on normal flow we would be running at 80 degrees, and so everything will be warmed through. On startup, in fact, when the reservoir pressure is very low, we don't have a problem because we can empty the pipeline quite effectively into the well, and then the pipeline will sit just in the gas phase. So the time when we have problems with two-phase flow is when the reservoir pressure is too high to be able to empty the pipeline into the well, and then you can get CO2 condensing in the pipeline offload. And when you've got CO2 condensed in the pipeline, when the slugs go over the well, over the platform, which we assume they will, then you'll have two-phase flow also going into the well. But we don't expect to get two-phase flow all the way down to the well bottom, because in those conditions we think the reservoir pressure is too high.
Okay, great. Thanks for that. All right, and next question is moving more on to injection, and the question is, how deep is CO2 normally injected? So that may be asking, I suppose, about other projects or specifically roads, so maybe you could talk to us about both.
I didn't quite get the question.
I think I can answer it.
You got it? Yeah?
Yeah, normally the CO2 is injected at a depth where it stays at high density, which I think is below about a kilometre or maybe 900 metres. Our well is much deeper than that. It's about 3.5 kilometres down. You want to inject at those depths so the pressure is high, so you get a high density of CO2. Otherwise, you need a large volume to store a relatively low amount of CO2.
Great. All right, our next question here is, will a CO2 purity of 95% be okay for transport and storage?
Do you want to take that one, Jan?
No, I didn't quite hear it good enough.
Okay. I'll say it again. I'll say it again for you, Jan. Will a CO2 purity of 95% be okay for transport and storage?
Yes, we think that there will be a slight influence on the thermodynamical properties of CO2, but they're probably not that high that it won't work.
Yeah.
We haven't much.
Yeah. We haven't done a lot of detailed work on that because our CO2 is 99.9% pure.
Okay.
So we've only looked at the question in the context of who else might want to put their CO2 into our system, and then it does depend what the other 5% is. But if it's nitrogen, then it's not a problem.
Is it corrosive? Then it might be a problem.
Yeah.
Great, thanks for that. All right, our next question is, during the first phase of the operation for well pressures from 30 to 73 bar, what is the CO2 injection rate? And will the capture plant be running at full capacity during this phase?
Yes and yes. The intention is to be able to inject at full flow. Mm-hmm. There's a possibility of a problem if the reservoir pressure gets very low for the first few weeks, but we believe that we will be able to inject at full flow, and therefore the capture plant will be able to operate at full load. And we've certainly modelled from reservoir pressures of 20 bar and upwards.
Yeah.
All right, our next question here is, what is the maximum flow rate of a single train CO2 compressor, and how many trains of compressors are included in your design?
We have a single train,
Mm-hmm.
and we didn't have a problem with specifications for this size of single train. So the 169 tonnes an hour is fine for single train. I don't actually know what would limit the suppliers. So I don't know the answer to that question, except that it's a higher flow rate than the one that we've got.
Okay, thanks. All right, the next question is, how do impurities like sulfur dioxide and nitrogen affect the power requirements?
Can you repeat the question?
Sure.
That sound is not very clear.
Okay, how do impurities like sulfur dioxide and nitrogen affect the power requirements?
You said nitrogen, and what was the other component?
Sulfur dioxide.
Sulfur dioxide.
Yeah.
That's difficult because sulfur dioxide might be corrosive, or will be corrosive. And the mole weight is different, so it will have a slight effect on power requirement.
Okay, so mainly it depends whether they're.
It's depending on the It's also depending on the quantity, of course.
Yeah.
Do you know a better answer, Andy?
Well, I think we would worry if we had 5% of sulfur dioxide.
Yeah.
But nitrogen is a reasonably light. I think nitrogen will have a significant increase in the power requirements because at high CO2 flows you won't get the same gravity head in the well. So I think nitrogen will have an impact. But we'd have to do the sums to quantify it.
Okay, thanks for that. All right, our next question is the quoted efficiency for the power plant pre-capture?
Yes, it's a lower heating value number without capture. It's just over 46%, which is very good. It's a very modern, very efficient unit.
Great. All right, and I think I'm coming up to our last question now for the evening, which is, what is the communication method between the platform and central control room of MCP?
We haven't worked that one out yet.
Okay.
It's probably.
That's a stay tuned, is it?
Yeah. Yeah. I mean, we think in normal operation, in fact, the platform valve will be controlling on pipeline pressure. So in normal operation, you in fact could operate with no control, with no signal going at all. But we will, of course, have signals for startup and shutdown and for emergency purposes. The existing platform is actually operated from P15, but we haven't worked out how we'll handle that.
Okay, that's great. All right, now if anybody still has any questions, you should feel free to submit them to the Institute through our email address, which is webinar@globalccsinstitute.com, and we'll find a way to get an answer back to you. A quick reminder that the webinar has been recorded and will be available on our website in the next few days, along with the slides we've used. And lastly, as you are leading this session today, we've put together a very quick 3-question survey and would appreciate you taking the time to complete these questions to help us improve our webinar program. I certainly hope that you found this webinar valuable, and once again I'd like to thank Jan and Andy for their presentation and for answering all of our questions. Thank you all for your attendance, and good night.